All right, so, yeah, okay, it's there. Hello everyone, so welcome to the third beginner lecture for competitive programming community here. Before we start, I guess we should just look out for our posting, the leak code questions. They're in our competitive programming channel. It's a thread in it, and in the thread you see the list of problems that we put out. And there's beginner and then there's advanced problems that you can solve. We suggest you try both. You pose your solutions for beginner problems and beginner solutions, and for advanced problems and advanced solutions. That's pretty much it for the leak code questions. Also, we had a binary search night last Friday. This Friday we won't have a binary search night, so we won't compete. Yes?
What is binary search?
Right, binary search is an alternative website to leak code where you're actually engaging with other people live, and you're competitively solving problems, and the first one to solve a problem gets a gold medal, the second one gets a silver, third gets bronze, and so on. And so it's a way to actually compete with each other live. We put the link out there. You have to make a separate account, an account separate from leak code. It's fun and engaging, and you do learn a lot by coding with other people. We do suggest that you attend. It's not going to be this Friday. It's going to be bi-weekly, so once every other week. So last Friday we had one. Not this Friday. Next Friday we're going to have our next binary search night to compete with each other. All right, so on to today's lecture. So last time we were going over sorting. I did not finish. I left out Quicksort, which is my favorite comparison sort, apart from Mergesort, which if you recall Mergesort, put this here for now. In Mergesort, you get the array and one, no, not that number. I'll put another one. Doesn't matter. And then you cut up the array into and again. Right, and as soon as it's a size 1, you don't do anything. But then, you cut this one up, and you're supposed to, iterate through each of the sub-arrays and see how they should fit in the original one. And we find that it's like this. And then we build our way back up, and we iterate through both, and we get this result. I'm not doing the whole thing because I already discussed it in the last lecture, so refer back to this to get more into the specifics. And this one down here, 5, 8. You can see? Okay. So then iterate through these, and you find out they iterate through this one and this one. So this is the smaller one, then this one. And here, the smallest one is 5. Yeah, and then here. What? Oh, right, sorry. Thank you. 7, 8, and then the last one is 9. Okay, so I didn't do it exactly like I did it before, but just refer back to that video. So basically this array cuts it up into halves, and it divides the problems and conquers it by, the sub-problem, the optimal sub-solution for the sub-problems. Okay, so this is an n log n solution. So the runtime is the size of the problem times the logarithm of that size. And I said before, this particular sorting takes O of n space. I mentioned space complexity, but it's extra, like it's an extra data structure you have to take up to solve the problem. So now I'm going to go over a different sorting solution that doesn't take up any extra space, and typically runs better than this. Oh, this is Mergesort, so just I'm going to erase this. So I'm going to bring the array closer. Put this at 5. Let me put okay, some random array that I picked, and we're going to solve it using Quicksort, right? And so I'm just going to show you generally what it's going to do. So first, remember before how we were cutting it up? Well, it's the reverse. We actually solve this whole thing and then cut it up later. So it's like the reverse merge sort in a way. So you keep a pointer on this one right here. We have left, we have I, and the point is that if it's less than, don't move. If it's greater than this value, don't move this, but move this up. And if this is, actually no, hold on. If it's greater than this, move this up. And if it's less than,
wait, what is less than and greater than?
well, basically you're going to end up with this being in the right spot, and everything to the right is going to be greater than, everything to the left is going to be less than. Let me actually refer to it.
If left is less than right, move I.
Hold on. What did you put? Don't look at the camera. Look at the people in the room.
You were supposed to read that out loud.
Well, I don't think they heard me, right?
I think the live stream did, but
The live stream did? Well, so, okay. Okay. Well, I mean, the live stream, they're part of this, right? Okay, so I'm actually going to call this P. Right, I starts here. J also starts. It's actually strange how they wrote it. It's actually really strange how they wrote it. So here's P. Yeah, this is really strange how they wrote it. So basically, if this is less than or equal to, right, you swap these two values. So at first they're the same, right? If this is less than this, you move this up, else move this one up. Right? So they swap with themselves. So now we're here, right? If this is less than this, swap these two. One and 5, there. And that was less than, so we have to move I up. And then we move J up, all right? And if this is less than this, do it again. So they're both up there. And then move J up. And out here. This is greater than this. So we swap, well, we don't really have to do that, but actually, it doesn't really matter. Right? And since this is greater than, we don't move this. But we do move this one up. Okay, now here. And it's less than, so then now we swap these two, move this one up, and now J is going to move here. And now the point is that, so like, disregarding this, what do we have here? Well, compare this with this.
Oh, the left is smaller than the right.
Everything in the left is smaller than the right. And now we get the leftmost value of the right and swap it out with the pivot. This is P, by the way. That's a P. All right. So it's still unsorted, right? However, we find that now 4 is here, and everything to the left of 4 is smaller than. But everything to the right is greater than. So that means 4 is in the spot it's supposed to be. We just have to do the same thing for the left and the right. So the way you break up the problem, that's unsorted. Okay, this is the pivot, and you don't do anything to that, because that's already in the spot it needs to be. And of course, the fact that I'm breaking it up means we're using recursion. So this function is going to recursively call itself after this looping of swaps, right? That I had to like manipulate the pointers in the array. So once you recursively call it, you do the same thing we did here on this side, right? So this is less than. Okay. And since this is only 2, just swap these two. No, sorry. And swap it. Less than. Swap. Greater than, don't move this. And then now we swap these two. Okay. And then of course, this one's gonna come out. All right? Look at you, yeah.
So pivot is always to the end.
Yeah, so pivot is always the last. And the point is that you're gonna end up with the pivot ending up in its actual spot in the array towards the end of this whole looping, of the pointer, moving it around. And this pointer, you only move it when it's less than, right? And this pointer always moves, the J. So this is a recursive function too. although it cuts it down differently. So the code, let me see, do I have space? Okay, I have space. It's like this. I'm gonna refer to this. So I guess one thing I should also point out is that this doesn't take up O of n extra space. The space complexity is constant. So it's only the amount of extra variables you need is like 2 or 3. I forget now. I'm gonna do it in Python. I mean, I kind of want to, I don't think I'm gonna have space for everything. I might have to erase it. Are you good with me erasing this, or do you want to keep looking at this? Okay. Yeah, sorry. It's just I don't have space. Yeah, I'll leave that the way it is. I think I have space. Okay. So this will only run if the start is less than the end. So let's say the start equals to the end. That means the size of the partition, or like, you know, where you cut it up, is just one value. And an array with one value is already sorted, so you stop. That's the base case, is what I'm saying.
So start will be equal to 0 and then
N will be equal to the size minus 1. So n minus 1, right? And then you're gonna have the pivot index, right? Well, the pivot, you know, is here, but then the pivot's gonna move somewhere in the middle of the array. So you're gonna call another method called partition. And the partition method is basically what we were doing with the pointers of moving it around. Oof. And here we go from start to end. Okay. So the pivot is going to be an integer value such that we want to call this again, right? On the left side. So we take the array and we start from the start again. And then the pivot is going to be the end. Or I should say pivot minus 1, because we're going to exclude the value that's already in the place it's supposed to be. And then we're also going to call it pivot plus 1, so the one after that value, to the end. So this part is the for loop part, and yes, Lázaro has a question.
here, so P represents the pivot.
Right. So actually, it was 4. If you remember, this was 4.
Okay.
And then towards the end, we found out that it belongs here. So basically what this is saying is that now Quicksort is going to be called on everything here and everything here, right? This is this call, and this is this call, right? Okay. So, well, we defined the recursive step. Now we have to work on this one, and this one was the whole thing with the pointers of I and J and the N. So I don't know if I'm gonna have space in this little spot beneath it. I'm gonna try, but I'm gonna try. There versus this part right here. Yeah, they reversed it here in this one. Okay. Actually. So in the for loop, J is the iterator. This is a Python for loop. Who's here comfortable with Python, by the way? No one else is here is comfortable with Python? So this is just a for loop. This is gonna be the J, and this is J equal to, like, say equal to 0, and then less than this end. So it's only gonna go from this value to the one right before it. And see, well, actually, since it is the pivot, I'm actually gonna put it as the pivot, since end and pivot are the same. So for J, from start to the pivot -1, we're gonna do the swapping. Also, I is very important, and we only move I if it is less than. If it's greater than, we don't move I. So just return it. Okay. Actually, now that I think about it, I missed a step. Sorry. And then so I wrote the rest. Okay, so this is supposed to be indented. This is a tab, because in Python you need to tab it instead of having the curly braces, because Python doesn't care about curly braces, they care about indenting. So that would be within the for loop, right? So from J to start, from start to pivot, right? If RJ is less than the pivot, so I think this was 4, we would move it up. We will move I up. Actually, let me put it here. Okay, yeah. We move I up by 1. So I is here, J is here, and if it's less than, then move it together and then swap them. If I and J happen to be the same, that means that value was already less than the pivot. Okay. But if it is greater than, or actually, yeah, or equal to, yeah.
If I is going to start with 0, shouldn't you be moving it up after you swap?
If I is going to be at 0, right, actually it should be -1. It should be -1, yeah. So I is going to be -1 at first, right? And then only swap when you find that it's less than, because you could be at a situation like, I'm gonna undo what I did before, and I'm gonna put 4 back. I'm gonna put 5 here, and I think this is a 3. You could be at a situation where you're here, right? You're at this, there's this 2, this is less than. However, you have a value that's greater than 2, so 5 is supposed to be ahead of 2. So here's J, and here's 5. And before, we did not move I, we kept I here, right? And so what we're supposed to do is we're supposed to swap these 2 out. You see, actually,
Is I here equal to a pivot?
no, the pivot is 4. Oh, the pivot is 4 at first. And then at the end, we're going to return where it actually ends up. Well, I was here, okay, and then 2 turns out to be smaller than this one, so we move I up. And then we swap, like right here. Two and 5, right? All right. So basically, here's the trick. I is always going to be before a value that is greater than the pivot. And there's a point to that, right? Because we want to kind of move all of the greater thans ahead of the less thans. Because we are sorting it. Does that make sense? Nobody's confused?
All the greater than, we want to move in front of the pivot, and all the less than behind the pivot?
Yeah, well, exactly. All the less thans are going to be to the left of it because they're less than the pivot. Then all the greater are going to be to the right. And I was watching myself on the stream just to see the live chat, see if they had any questions. Turns out they don't. So that's fine. That's completely fine. Anyway, yeah.
Wait, is partition finished?
Yes.
Can we walk through the example of that already?
Yeah. So basically, well, I kind of moved up ahead, but we were here, right? And we swapped it. So we moved J up, and J is always moving. And see, I is always before a number greater than this one, right? So then we see that it's less than, so now we are able to move this up, and then we swap the 2. So see? That was a bad 3. Let me write that 3 again. See? I still stays behind this 5. We move J up, and J is not less than this, so we don't do anything. And then J kind of, we don't want it to become the pivot, so we stop. Okay, I'm doing this in case there's another 4, in case there's another, but I just put that there just cause. But we're just gonna assume that there are no repeating values. Let's just presume that there are no repeating values. All of the array values are unique.
So we can remove the equal to when it's unique?
Fine. Dale, yeah, whatever. There. I guess because they're all equal to, then yeah. I'm sorry, Lazaro. You're my friend. So anyway, now I is here. I is always before a value greater than this one. So that means that towards the end, we can swap pivot with the one after I, right? So we swap 4 and 5. Now 4, where it used to be, now everything to the left is less than, and everything to the right is greater than. And then we return whatever this, which is I plus 1, we return this at the bottom. All right? So in a way, when you cut it up, doesn't it look like it was cut in half? Do you kind of see that?
Because we know the 4 is supposed to be there.
Right. Will this always happen? Would it always be cut in half? What do you guys think?
No.
Why?
Because it could be repeating numbers.
Okay. No, Forget the repeating numbers. That's inconsequential to the question.
Depend on the pivot.
Right. So it depends on the value of what the pivot was before. So let's say, I don't know. The pivot is an extreme. Let's say this was 1. Let's pretend that actually and 5 has to be somewhere. Let's go through an extreme one, actually. An extreme case. 4, 3, 2. So this is an extreme case. So the array is sorted, but in the reverse direction, right? What's going to happen then? Well, you're going to be at your pivot. It's 1. Here's I. Here's j. All the numbers are greater than, so you just move j here. So you move j here, right? And you see that the one after I is greater than I. So see, I is always before a value greater than the pivot. Then you swap it out. Since 1 is the smallest value, it's going to stay at the left. So what did you do? To the left is nothing. It's nothing. And the right is the whole array minus 1 value, which is that one. So imagine we kept doing that, right? Let's say here we this isn't 5. Let's say we ended up with 2. Then where is this going to end up if this is the smallest? So the 2's are just going to go here, and then you're going to go through another for loop. This was 6, I think. Imagine that you keep for looping, like, in a way, this becomes a bubble sort. If you're not careful, this algorithm will turn into bubble sort. And the bubble sort is the worst sorting algorithm. Okay.
So before we do quicksort, to combat this, can we go through the whole array and then find the median?
The median?
Yeah. And then remove that median after we sort it.
What do you mean?
So we know that we're gonna land exactly in the middle.
We want to land in the middle, yeah.
Yeah. So before we call quicksort, go through the array, find the median value,
Okay.
then sort the array with that new median value that you added, then get that answer, and then with that answer, then remove the median value.
So you tell me to find the median before.
Yeah, and then remove the median.
So how do we find the median before we get to quicksort?
We go through the array.
Okay. So then now when we cut up the array into partitions, do we have to do it again? For each partition, find the median for each part when we cut it, the left side and the right?
No.
No, so just as a starting point, you find the median, and then
Yeah.
the rest is just normal quicksort.
Oh, so you want to find the median.
So we know that our pivot would be, and then add it to the end, append it to the end, and that way we can ensure that our pivot will be in the middle.
Okay, so we want to just find the middle and put it here to make sure that when we're doing this, it ends up in the middle.
Yeah.
We could do that. So you're saying to actually go through the array?
Initially.
What if we didn't have to go through the array? What if we didn't have to do that? All right, we were on the same page. We were on the same page. We don't have to go through the array.
Well, no, you can just take the first value, the last value, and the one in the middle, right?
What do you mean?
So if you take the first,
No.
no?
So let's say the first value, last value, and the one in the middle, or the 3 smallest values.
Damn.
Yeah. So there's actually a way to do this. You gamble.
In that
It's-
case,
it's-
God's against you.
Yeah. No, don't worry. When you're gambling for the median, you have pretty fair odds. Like rolling a 7 is actually pretty easy because that's the most common roll. So, okay. I don't know.
Wait, what? How does that
Yeah, rolling for a 7 is the most common roll of the dice.
That's true. What?
He's confirming me, yeah.
It's on.
Exactly. If you actually do the math, it does show that
A7?
a7 is the most common.
They're not all 1/6?
No.
No,
Well,
you roll two, like,
So
Oh,
snake
two
eye.
dice.
Two dice, two dice, two
Oh,
dice.
okay,
When
yeah,
you roll the dice,
I got
two.
it. Okay.
Roll of the dice.
Okay.
Because if it was one die,
Statistics class right now.
it would be, if it was just one, it would be one die. Two is dice.
Yeah.
Language. So let's say we were one here. Let's say this is 6. So what can we do to make this better? Well, we want to put the middle here first. So what we're gonna do is gamble. But like I said before, gambling to get the middle is actually the odds are in your favor. So what can we do, right? Let's say we picked a random number in this range, right? What are the odds that a random number you pick is the middle? Rather than it not being the middle. Like being in the extremes. Like at the greatest or the least. What are the odds that you're going to find the middle?
1/n.
Well, that's technically right, but what's the odds that... Oh my God. Well, what's the odds that you're going to land in a range that is 20, I think it's 25 percentile? Is that how it works? You know the box and whisker plot?
Oh, yes.
Yeah, so there's this thing where
Just
I think I need to kind of move here. I need to move here. So
it's just unlikely that you're gonna get an extreme if you.
Okay.
So how it works is that this is the middle value, right? And everything here in this box is 25% of the values, and everything here is 25%, right? And then the rest is the other half, 25%, 25%, and then you might find some extremes there. But what I'm asking is, between here and here, right? Half of the value is already going to be contained pretty close to the middle. So you may end up, getting a value here. Maybe it's here, but it's close to the middle, right? And that really makes it similar to cutting it down in half, right? Instead of cutting it down like this and then this and this, like instead of doing this, because we're trying to find a random number to get close to the middle, it makes it easier to cut it down right in half. Even if it's not perfect, but it will happen. So how do we do that? So I'm not going to use a Python method. I'm going to make it up because what?
Was the answer like m times 2 over n?
M times 2 over
Or
n.
m is like the range. Say that you want plus or minus 3,
Mm-hmm.
then the closest middle. So 3 times 2 is 6. So it's 3 to 11.
But that's the thing. We're going to get an index, right? And we're hoping that index value is the middle. Like the actual value that index is at is the middle value to actually cut it in half, more or less in half. Average it out. It's not going to be perfect, but so let's say here I did rand piv equals rand int between the start and the end minus 1. Well, actually, so random integer from start to end, and end is not going to be an option because it's left out as always. But it's going to give you a random number in between. And then you swap r okay. So then you swap the array, the value at random pivot that we just did, with the array value at the end. Actually, I did not write this properly, I'm sorry. Okay. So you swap the array at the random pivot, some value in the middle, or maybe that value is the middle value. This is actually a gamble. But odds are, because of that whisker plot, you're going to be close to the middle. Like you're going to find the value close to the middle. So you swap that out with the array pivot at the end. And maybe this will be 3. It's not 4, but it's close. So that's the thing. If you find that extreme, you're going to swap the extreme, like 1, and swap it for a value that's pretty close to, say, 4 or 3. So you swap it, and then after you're done swapping it, you do your partition algorithm, and then hopefully you did actually cut it down the middle, and you have an evenly sized, they're more or less the same size sub-problems that you have to solve. Is anybody confused?
I have one question. Earlier you said that we have to be careful because it could become bubble sort.
Yes.
So to avoid that,
We do
we
this.
have to do the random.
This random pivoting, this is randomized quicksort. This is what keeps it from being bubble sort, at least to the best of its ability. Because this isn't 100% guaranteed, but it's possible. So also one other thing, what is the time? Well, the time complexity is the same as if we are cutting it in the middle and solving sub-problems. This is big O of n log n. So this is log linear, right? And this is supposed to keep it that way. This is to keep it from becoming n squared. Because remember, this could become bubble sort. So, well, any questions about that? You have a question about? No, no, you don't? Okay. Okay, so this is to keep it from becoming bubble sort and n squared. And typically, this actually runs better than merge sort, generally, which is actually why I like it more, and it's less writing. Yeah, okay.
Actually, I have a question. Even though we're doing a random integer, we can still do, it can still, it's less likely, but it can still happen that we will end up with bubble sort, right?
Well, actually, you're right, but it's very unlikely.
Okay.
So statistically speaking, mathematically speaking, this is like theory.
Be less likely to happen.
Yeah, this is completely theory, like algorithm theory. This will make it n log n. This will, make it like that. Also, this random integer from start to end is going to be a constant runtime. This is constant, so this doesn't eat up into it. What was I saying? So what's the space complexity? How much extra space do we take up running this algorithm? How much extra space? Yeah, here. How much extra space?
This one?
Yeah, this one. Yeah, this one.
Nothing.
No, you do. You do take up extra. Well, the array is already there, but that's not extra space. You're already working with the array. Do you have to create another array, like in merge sort?
What do you mean by extra space?
Like, do you have to create an extra array or an extra data structure?
But you're doing this in place.
Yeah, we are doing this in place. We're doing this in place.
So this is nothing, no?
No. What about these? What about these?
Those are indexes. You're still using
Yes, this is a value. This is a variable that's taking up space.
So wouldn't it just be a constant?
Yes.
Yes, that's what I'm saying. It's
That's
constant.
what I mean by
You said
nothing.
nothing.
Yes, that's what I mean by nothing.
That doesn't make sense. That
Like,
doesn't.
You're not adding extra. You're not
I wish we had a
adding
mic
anything.
for Lazaro too, so that they can hear our conversations.
Dude, nothing should be equal to all of one.
This is O of 1.
Yes.
This extra space is O of 1.
Okay.
Yeah,
Yeah, it's constant.
yeah.
So
That's what I'm saying.
Is
But-
it extra space then?
it's
It
not.
is. Well, I mean, it is, but it's space that does not grow with the problem.
Exactly. So
Yes.
it's negligible. So
It's
you
negligible
ignore it, so it's
space.
nothing.
Okay, in merge sort, we have to create a new array copy, right? I'm going to come here so that they can see me. You have to create a new array copy every time you run it recursively. So you have to create extra space, right, to fill in the values again and have a sorted partition. Here, the only extra space you need are 2, maybe this integer, and that's it. And it's a finite number, 1, 2, 3. Versus when you're creating another copy of the array, well, that's dependent on the size of the array. So that's why it's O of n extra space in Mergesort and constant in this one. Okay. All right. Do you guys mind spending 10 more minutes here? No? If you have to leave it. Okay. This is better than Mergesort. This is the undisputed king. And now I'm going to talk about stacks finally because I'm erasing this. If you want to refer back to this, the live stream is saving this for us. Okay. All right. Okay. Okay, stacks. All right. Okay, so we were gonna go over binary search, but we don't have enough time. But we did go over it in the very first lecture. When you have binary search only works on sorted arrays, right? And if you're trying to find the value, it takes log of n because you're just cutting the array in half, seeing if it's greater than, you check the right half. If it's less in the middle, you check the left half, and so on and so forth until the left and the right ends are the same. So you narrowed it down to one value. Okay, that is binary search. I'm sorry I couldn't go more into depth with it because we're running out of time. Okay, a stack. So do you know what a stack is as opposed to an array? So
It has like goes in, like the first goes in and then the last goes out.
so the first goes in, the last goes out?
Yeah.
First in, last out? Yeah, Philo.
What?
First in, last out.
Really?
Yes.
No, first in is in the front and last out is the one in the back. Isn't it?
Let's conceptualize it. Let's conceptualize it, right?
It's last in, first out. It's like
Okay. For that is for queues. That is for queues.
I don't know what that is now, but I know that they have like first in, first out, first in, last out, and something.
Right. So the first value you put into here is going to be there. Okay, can you see this? Can you see that?
LIFO and LIFO, right? I think what you said is right, but backwards.
Really? Because if it goes first in and then the last.
Listen.
that's the one that you put.
Listen, here's
The first one.
the first one is red.
Like I remember when it was taught to me, think about it like when you're like at the
Oh.
bank.
All right, we're having a whole discussion about whether this is first in, first out, first in, last out.
You're right.
I'm just going to draw it out.
Okay.
You're right.
Okay, so I'm making the stack, right? I'm color coding it.
I had it by hand.
No, but it's
Okay.
first in and last in.
I wish we had more colors so I can better demonstrate this. I'll make this one green.
Yeah, it's last in, first out.
Yes, you are right. It is last in.
First out. Yeah.
Yeah, it's last in, first out.
Yeah.
I don't think it's not first.
Okay, so the first one, which one was the first one we pushed to the stack? The red, this red one. Okay, then we put this green one on top. Then you put this blue one on top. Then we put this green one. What was the last one we put in?
Green.
So this is the last one, which is the only one we can remove from the stack.
The green one.
First in. And the first in is the last one to go out.
Yeah, but that's not the acronym.
That's not
But
really
the
how it
acronym
goes.
is
Philo.
No, it's
No.
not.
Why are we arguing about this? No. Convince me that this is not Philo.
I looked it up because I also get confused.
LIFO. First in, first out approach.
Just look at at the end it says Q or stack. And yeah. I also get really confused about this.
I'm right. I'm right.
LIFO is for stack and FIFO is for Q.
I'm saying that Philo is for stack. Philo, LIFO is the same thing. Philo and LIFO are the same thing.
But that's not the acronym.
But the acronym is LIFO.
It doesn't
They-
matter.
They have it like
Okay.
FIFO.
We're having a whole argument, guys. We're having a whole argument.
It's the same thing. It's the same
It's the
thing.
same
LIFO. Okay, so they're the same thing. The first one in is the last one out.
Yeah.
This. Oh, I should have colored it differently. Whatever. It is what it is. What it is. So, first one in is the last one to get out,
Yeah.
and the last one in is the first one to get out. So this green one can get popped. And now it's not in the data structure anymore. It's somewhere outside. You use the value. Okay? So the main things that you can do with stack is, let's say, stack.peak. So stack.peak just looks at the the last value you put in the top, and it doesn't take it out. Shut up, Siri. And stack.pop actually removes it, so it would just take it out, and then I'll just put it there.
I have a question. Like I learned that from Java, but I know you talked about Python. Is that like the same? Would it be the same in Python?
Okay, so in Python, the list is what we use for stacks,
Okay.
and the list is also the same thing we use for queues. It's just a different way to actually work with the list. It's its own thing.
Okay.
It's like a whole. There's a Python workshop coming up, I think. There's a Python workshop tomorrow. At what time, last? Actually, let me you're hosting it?
I think it's 4.
Wait, you're hosting it?
Yeah.
How do I not know this? You're my colleague.
No, because I didn't even know until yesterday.
Oh, he didn't know until yesterday, guys.
Yeah, the Python is from 4 to 6.
4 to 6 tomorrow. There's a Python.
Oh my god.
That's great. That means you guys are gonna get into Python. You're gonna solve everything in Python. Honestly, it's less writing, and that's what I like. That it's less writing than Java or C++. So let's say in Python, I would say I would do it like I would do this for peak. So this -1. So see, only Python does this, guys. They can wrap around. It goes around. So 0 is the first, and then if you go back 1 to -1, it's actually the last value in the list. All right, we got that. Does that make sense? Okay. And then this pop would be, so Python does have a pop method, but it's looking for a particular index. So let's just put -1 like here. -1, remember? It wraps around. So it will just take out the last one. Oh, and of course we have push. And then we will put value. And let's say value was this blue mark, whatever. And we pushed it right back on top. And then, well, we know about the, stack. Since it's a list in Python, you would do append. Append would be append value, put to the end. Okay. I was gonna do a stack problem, the valid parentheses, but we were really out of time. I don't even know if we can do the queue anymore. We can?
10 minutes.
We have 10 minutes. Okay, queue.
I think 15, sorry.
Oh, okay. We have a bit more. Arguing about this stuff. I don't know why we're arguing about this. You know what? I'll put this. So the stack was Philo, right? The queue, by contrast, is FIFO, all right? So the first one you put in is actually the first one you get out. So it's like a stack, but it's a reverse stack. In the UK, right, this is weird tangent, I know. In British, they call lines, like a line to get into, like say a restaurant, a bar, a nightclub. They say get in the queue. They actually say it like that. It's a queue. It's a line. So the first come, first serve. First person is the first person served. So I would, do this. I'm gonna actually be a little creative with my queue here. So you're getting into a movie theater. Yeah, I wanted to do this. Person number 1, person number 3, person number 2. The numbering is arbitrary. I just gave them random numbers to differentiate them. Okay? So they come in like this, and they go out like this. Versus with the other one, they come in like this, and they go out like this, right? So there's one entrance, and there's one exit, and they're different from each other. But the entrance and the entrance are the same. So if your path is blocked by another member, you have to wait until that member is out. Here you don't. You actually have to wait to get out for the people who came first. FIFO. So, if I'm mistaken, Q is also has a push, right? Yes, okay, yes. Q has a push. Q has a pop, and the pop's the first one that came in, as opposed to the last one. And it also has like a peak. It's the same as a stack with the reverse direction. So I didn't talk about the okay, yeah.
So it's the same as a stack, but what's the difference? Like where would the push?
The difference is that the first one that comes in, you can actually access that value. You could remove that value, as opposed to the last one where it was in the stack. The last one's the one you remove and look at. Here, the first one's the one you look at and remove. And you push to this direction, you pop from this direction. But in the stack, you push and pop in the same direction. Okay? Okay, all right. Are we confused yet?
Couldn't I just do the -1 wraparound in the queue?
Oh,
like
the
remove it?
Python?
Yeah,
Okay,
remove the
okay.
stack.
But let's pretend in Python we cared about this. Because in Python you can manipulate lists to do whatever you want with them. But let's say for the sake of this lecture, we cared about what our lists were doing and we wanted to follow convention. All right, because in Java, there's an actual queue data structure. It's not just, I can manipulate arrays, however, you can't. Arrays are, well, they're immutable. I think they're immutable in the sense that you can't change its size, or C++, like in some regards. You can't change the size. So well, you could create a queue or stack class on your own, which is usually how you learn about them, and then you would say make it an array. Also, the thing about wraparound, you would need to know that if you're making a queue class. I'm not going to get into that though, because we don't need to know that here for this lecture. So one application of this is breadth first search, and that is basically that is a way to traverse a graph from a starting source. So I'm going to say, I'm going to do it here.
If you want, you can do, because I know we'll be doing this concept in other lectures, but if you want, you can do binary search now. You have 10 minutes.
Are you sure? You don't want me to go over this?
You'll be doing another lecture if you want to. It's your call.
What do you guys want to go over this or binary search? Only because we have 10 minutes. It's just the thing. I kind of went over binary search already in a previous lecture. Okay, so I'll just go over this again. It doesn't matter. So DFS goes in this direction. and so on. So you're yeah,
What's DFS?
depth first search. Yeah, DFS is depth first search. You see my face? Oh, but you need to see this. So DFS is depth first search. So you go down the depth, and then once there's no members left to go down, you would go back up. You know, you would backtrack and then go down, go back up. All right, and then just go back to the start. So they're going down the depth of the tree. Well, I mean, it could be a tree. I made it a tree just because we know what a tree is, right? Or we don't know what a tree is? Okay, all right, so this is a node, and it has children, right? And the children could be contained within a list of child nodes. And you recursively go through each child node in DFS. But in BFS, you don't use recursion at all. Kind of why I like it a little bit more, because recursion does take up the recursive depth stack in programming, and now Lazaro's nodding his head, because he knows I'm going into complicated stuff. But DFS is better, you think? No, man. BFS takes up less memory. Come on. But recursive takes up like the whole recursive depth. You could reach the limit with. We'll talk about this later, right? Yeah, we will talk about this later. So basically, in BFS, which the path, I will put it in red. It goes like this. All right, do you see the difference between how we did DFS, which was going to, but here in BFS, you're going by level. So how does this work? Well, let's say we process this one first, and then we push all of its children after that. And then we pop that out and work with the next first element, which is this one. And then we push all of its children, and then once we push all of its children to the queue, we pop this one. And so on and so forth, right? But we know that the one after this is the one next in the queue, which is this one, not any of these, right? It's going to be its sibling. So do we have enough time to write the code?
You can write the code for that.
Okay.
Yeah, you have 7.
7. So this is like a for loop or a while loop. So this would be, I'm just going to say call it the root node while q. So this is saying while it's not empty, while, this is Python notation, and I know it's, if you don't know Python, this will be a little confusing. But while the queue is not empty, right? You put, current node equals queue.pop, right? And then the current has a list of nodes that you iterate through. For node in, well, maybe you don't call them children, you call them neighbors. Right? Q dot push. So for each neighbor you find, so these two, you push them. And that's it. You push them, you get out, and well, that's how you traverse BFS. Right? And then maybe you want to do stuff with values, I don't know. This is as opposed to doing it recursively, which I'm saying, I disagree with Lazaro. I think this is better than going through a graph recursively. I mean, you may not always be able to do this depending on the problem you get. But if it's something simple like traversing, I prefer this. And that's just my personal preference. I think we're out of time already. 5 minutes? I mean, we could go over binary search really quick. I'll go over the concept for binary search really quick.
I mean, you wrote the code for DFS. Why not do the DFS?
Oh, actually, maybe I'll do DFS. So this is a quick preview into our next lecture, which is on recursion, right? No, I know what I'm saying, Lázaro. We really do need a mic for both of us, so they know what we're talking about. I'll write it in green. So DFS works like this. So I would say call this current node. Okay. So this is a recursive function that takes in the current node, and then for each node in current node.neighbors, which is a list of nodes that it would have, we DFS on that. All right. Oh, and yes, of course, you do need to make sure that you've already, visited it. So let's say we had a hash map or a dictionary. If I'll call it map actually. Call it map. If map dot and it's color coded. If it's not white, not equal. Well, actually, no. You do it if it is white. If it is white, you do DFS traversal on it. DFS node. Okay. So for DFS, the reason I did this is so that we don't go over a node we already visited. So we will keep like a map or a hash map, a dictionary, whatever you want to call it, and then for that node variable, value we're on, right? We would color code it. And if it's color-coded white, that value, then that means we haven't traversed it. So we call on it. And then as we call on it, we would turn here. Once we've already traversed it, we would set it to gray, right? Or black.
I think gray before you call it, so it's processing, and then black after you call it.
Right. Wait, in the for loop?
Inside of the if statement, you do like node is equal to gray.
If map, no, but you only do DFS traversal if it's white. Because if it's gray, you don't.
If you know it's white, set it equal to gray, as in it's processing, then call it. And then after the call finishes, you set it equal to black now.
Okay, all right. I'm gonna go. Right. Equals. So he's saying that it's being processed, right? So you're currently doing work on it. And then you call it. So let's say that this node points to itself. It could very well point to itself and you're doing this infinite like looping around on itself. So you point to gray so now it's not going to be white. You don't go back on it, all right? And then once you're done with that node that you already worked on, you would set that equal to, what is it, black. And once the node is black, you're completely done with it.
Then wouldn't it be inside the if statement? Because let's say if it does point back to itself, it will change it from gray to black, but you might still be processing its children.
So wait, would it go outside the for loop?
No, inside the if statement.
Inside this? Inside this?
Yeah, like just after the call now.
Are you sure?
Oh no, it's outside the if for loop. Yes, yes.
So actually, so we're both wrong.
Yeah, yeah.
So Lazaro and I are both wrong about where to make it black. So outside the for loop, that means we're done with the node. We're done with the node and presumably its children too. Its adjacent neighbors. Make it black. So any node that isn't white, we don't traverse it. We don't go back on it. Is it the same thing?
Because we do something for what else?
The point is that we don't traverse it. We don't do a recursive call if it's not white. We only do a recursive call if it's white.
Still doesn't make sense because we find node, and node is only available inside the for loop.
What do you mean? Node.
Node outside of the for loop, you don't have access to the for loop.
Yes, I do. Here it is.
Like for setting it equal to black, that's outside the for loop. Isn't that what you said?
Right. This is a node. Sorry, guys. This is current node.
I think those will be the same thing for gray before the for loop.
What? What do you mean gray? I do it inside the for loop. So this is for each node. And then before we call it recursively, we turn it gray so that we don't it doesn't infinitely call itself. And then this part where it's outside the for loop, we say that the current node we're on, we turn it black, we're completely done with that. We don't touch this one ever again. Okay, any questions on the difference between these two? No questions? I think that means we're confused, right?
For sure.
Pretty sure no questions means we're stunned in silence. We're in stunned silence.
Good thing we will come back to this.
We will come back to this, guys. We're gonna come back to this at later down the line. So, but this is recursion, and we are gonna discuss this next lecture, next Wednesday. And this was one application of using the Q data structure in terms of navigating a graph. I mean, this is just a graph in the end. Okay, so all right. So if we don't have any more questions, we don't, right? We don't have any more questions. Okay. I'm erasing this then.